Welcome back. Today we're going to start off by, I don't know, giving you my quick Kubi's hints for working in teams, and then we'll get into a few other things. But just to give you a quick review of last time, if you remember, we talked about monitors, and our justification was really that, well, semaphores are great and all, and you can do anything you want with a semaphore. There's multiple ways to use them, and ultimately, if you put those multiple ways into the code, they get confusing. So you can both use them for mutual exclusion, which meaning locking, or you can use them for resource constraints. And the cleaner idea was basically separate those two concepts into two separate types of things. One, the lock is for mutual exclusion, and condition variables are basically for doing the resource constraints, and that's what we call a monitor. So a monitor is a lock in 0 or more or 1 or more condition variables. I kind of put the 0 in there every now and then almost as a joke. I guess it's possible to call that a monitor, but it's probably just a lock. But certainly 1 or more condition variables in a lock gives you a monitor. And yeah, question? Well, I'll actually show you in a second. I would say that monitor is a lock plus the condition variable. So we'll talk about Java in just after I give you my hints for project teams. But the thing that I want to give you philosophically here is a monitor is a way of programming. It's a paradigm, not necessarily a language construct, which is the way a lot of books describe it. You can put monitors into a language, but you can perfectly well use monitors without them being native to the language. You could just have C++ classes that give you monitors or something. So I really want you to think of monitors as a paradigm for programming rather than a specific language feature. So the lock gives us mutual exclusion to the shared data. You always acquire the lock before you touch the shared data. You release it afterwards. The condition variable is a queue of threads sleeping inside the lock. Okay, and I made a big sort of comparison between that and semaphores, where you definitely do not want to go to sleep while holding a lock with a semaphore. That's actually what you're supposed to do with a monitor. You're supposed to go to sleep on a condition variable inside the lock. Okay? Okay. And then the other thing was, you know, you could kind of think of monitor, since it's a programming style, as here's a structure. You know, grab the lock. Well, the condition is not quite right. Wait. And always do that in a while loop because we have to assume Mesa scheduling unless you're told otherwise. And then we unlock. We do something. Again, at the exit, we lock. We signal people that might be sleeping, and then we unlock. OK? And were there any questions on this basic structure? Yeah, go ahead.
You always have to unlock before you can.
So your question is, do you have to unlock here and relock there? You know, you don't have to, but oftentimes, if you look at the reader-writer example, the reason we unlocked here and relocked there was this do something was very long, long-lived process of some sort, like going after a database. And really, the conditional variables that the monitor was protecting were kind of the access control to that database. And so we don't want to hold the lock on those for very long. Okay, so yeah, well, you could probably get by with not unlocking. Turns out in the reader-writer you could get by with without unlocking here and relocking. You'd find in the reader-writer example you don't get any of the interesting parallelism out of it because now multiple readers can't get in and so on. Another question. I will, again, synchronized, I'm going to talk about that in a moment. That's just an implementation of monitors. We'll talk about that in a little bit. Synchronized is a way of grabbing a lock, basically. Any other questions? OK. So hold that thought. So today we're going to give you some quick tips for working in project teams. How many of you had 100% functional teams? OK. How many of you did not have 100% functional teams? I'm going to assume that all the rest of you who didn't raise your hands had some contention. That's normal. After I talk about that, then we'll talk about language support, which will include Java a little bit, and then we'll dive into another topic, which is deadlocks. So we have a lot to do today. We'll see where we get. So, you know, what is it about a team? Well, why do we have teams in the first place? Well, unless you're talking professional sports where the number of people that are supposed to be on the field is somehow, you know, part of the game. The reason you have teams is because usually one person is not enough, and multiple people are enough. Okay? And the problem is that you've got to deal with the fact that every person is a little different and communicates a little differently. So big projects, you know, require more than one person. And if you look at a big operating system, there's thousands of person years involved. Okay, I told you about 60 million lines of code in Microsoft Vista. Okay, that's a lot of code. Okay, that's a lot of people tearing their hair out or drinking coffee at Microsoft to make this work. Okay, now it's very hard to make software teams work correctly. If you had any strife in your teams, this is normal. Okay, in fact, I have yet to see a software team that's truly strifeful at times, okay? Usually has to do with how much coffee has been consumed, but that's another story. So it's kind of interesting to contrast software with what I would say extreme hardware, okay? Big construction projects. The Empire State Building, it was a huge project at the time. It was finished in 1 year. And it's truly amazing what they did. They staged iron production thousands of miles away. They built sort of a pipeline of materials, and they put the thing up, and it just, you know, it's still there, which is good. And it, you know, it was quite the building at the time. The Hoover Dam is another example. Basically, they built whole towns to hold the workers, and they coordinated everything and brought all the materials in, and they built the dam, and then they tore down all the extra stuff, and they were done. It was fine. Okay? So software somehow just never is quite so smooth. And I'm not sure whether it's inherent or not, but it's just the way it goes. You might ask yourself, okay, well, software is not so smooth, and therefore missing deadlines is inevitable. Is it okay to miss a deadline? Well, we make it free for up to 5 days worth of deadline on your code. That's our slip days. In reality, slipping releases, although it happens all the time, tends to have an extreme expense associated with it. Okay? It's kind of funny, I guess, in a sad sort of way, that we used to make fun of Microsoft Vista for every year that it was supposed to come out, right? It was going to get released, going to get released, going to get released, going to get released. Finally got released. Huh? Yeah. Okay, StarCraft 2. Yeah, that's possible as well. So, you know, the problem is you lose not only reputation, but you lose money. Potentially, you lose contracts and so on. And so it's kind of a good thing to figure out how to keep your deadlines rather than skip them. So what's a big project? Well, I would say a big project is any project where time or work estimate is hard. Okay, if you can't figure out how long this is going to take, it's probably a big project. Now, of course, you couple that with the fact that programmers are eternal optimists, and you got a bit of a problem. You know, I had a grad student once, and this is so burned in my brain, and we used to joke about this for all the rest of his time there. But in his early days as a grad student, we were working on a paper, and there was some piece of data we desperately needed. We had a deadline at midnight. We had to submit the paper, and he's like, okay, just 10 more minutes, you know. And 10 minutes later, it was 10 more minutes, 10 more minutes, 10 more minutes. And of course, we were actually done 5 minutes before midnight, but it was not the 10 minutes, you know, after 6 or whatever it was when he first gave me that estimate. So the reason we bug you about starting projects really early is it's very easy to be optimistic, and programmers, especially ones who haven't been programming for 20 years, and I don't see anybody here who I think has been programming for 20 years. Maybe you did in your cradles, I don't know. But probably isn't that great at estimating time. Okay, so take that into account. Assume that if you think it's going to be done in a day, it's going to take 2. Okay, that's just the way it is. Now, can you partition projects? Well, this is where getting in a group is kind of fun, right, or interesting, because you got this thing that's got to get done, and the trick is you got 4 or 5 people that are trying to do it, and how do you divide up the work? You know, well, Joe will do the programming, and we'll bring coffee for him. Okay, well, that seems to be misusing the notion of a group, okay? Although Joe will be very wired. I don't know, maybe bring him 5-hour energy or whatever these days. So partitionable tasks, in theory, decrease in time as you add people. Is that true? Not necessarily. Of course, if you require some sort of communication in order to make things work, you know that you can't keep adding people because eventually the communication gets in the way. This is actually true of parallel software. Okay, any of you who have ever written parallel software, you're starting to get into that mode. If you haven't, it isn't the case that you can throw 1,000 processors at everything and get it to be 1,000 times faster. In fact, it might be slower. Okay, and it's true with humans too. Okay, you know, there's this mythical person-month problem, which is you estimate how long a project will take. It starts to fall behind, so you add more people, and as a result, you're more behind. Okay, this is pretty standard. It used to be actually in the big boom in the early 2000s that all these internet companies were promising things at a ridiculous rate, and so what they do is they'd hire all these outside consultants, and they'd end up more behind than when they started. Okay, so you got to be aware of this problem. I actually gave you the standard joke, you know, if one person can dig a post hole in 60 seconds, then 60 people can dig it in 1 second. How likely is that, right? So there are actually a couple of ways you can partition tasks, and I'm going to give you kind of two meta structures that you could have for your group. One of them is the functional structure, and here it's sort of, you look, you've got problems 1, 2, 3, 4, 5, 6, and you say, well, person A does this, you know, threads, person B semaphores, person C locks. Okay, that'd be kind of the functional partition. How many people chose functional partition for their groups? No, not so much? Okay, so the problem with this is there's a lot of communication across APIs potentially. If B changes the API, A might need to make changes. In fact, there's a very funny, not so funny story. There's a very large airline company, which will remain nameless, spent about $200 million on a new scheduling and booking system, and it was divided across 2 sites. And the 2 teams were working together. So after 2 years, they went to merge the software, and they found that the interfaces had changed, and the software didn't fit together, and it cost another $200 million to make it fit. Okay? So this is an API problem. Now, how many people remember the very famous one team working in metric and one working in English units problem with the Mars rover that sort of cratered its way down onto the Martian surface? It landed all right. It wasn't very functional afterwards. But if you don't get your APIs right, then the functional partitioning can be a problem. So those of you that raised your hand that you were doing functional partitioning, I hope that you have regular meetings on APIs. How does the 2 parts of the project, how do the 3 or 4 or 5 parts of the project fit together? Okay. The other kind of meta divisional is sort of a task oriented, where person A does some design, B writes code, C does testing. Did anybody do a task-oriented division? Okay, so now there aren't too many people. So, okay, now I'm a little confused as to what's left. Okay, now hopefully, how many people have one person doing all the work in their group? Uh-oh.
I was decided through a fair process.
I see. It was the short straw. So this is challenging. This is probably closer to what companies do, but it's hard to get the right balance. You know, the idea here is you focus on the strengths of the people involved. So maybe some person's a really good hacker, so they do the implementation. Some other person has a better broad view of everything, and so they kind of do the systems design. You know, actually, if you most companies actually have quality assurance teams, right? So you have a whole department whose job it is to take the code that is hopefully working and find the remaining small number of bugs in it. Now, usually what happens if you've got a badly designed system like that is you hand really buggy code to the quality assurance team, and they spend all their time finding really stupid bugs, you know, that you should have caught in your initial testing. So these are two options. I'm certainly open to other ones, but I thought I would suggest these to you. I don't know, did anybody sit down and actually think, well, how are we going to structure our teams? Was there anybody that went that far? So you know what happened in getting your design doc together. That's your first sort of key goal. And now maybe what you want to do is do a little bit of a step back and ask yourself, how did the process work? And should we structure our teams differently? And we actually have people that will try one type of organization and they'll go to the other one afterwards. Or, just because you pick something on project 1 doesn't mean you have to do it on project 2. Okay? I would say, despite the fact that not as many of you raised your hands as I would thought, most of the teams actually end up dividing something functionally. They sort of say, okay, you're going to deal with the boat problem, and you're going to deal with this, and you're going to deal with that. The trick there, though, is getting your APIs right, and that's the part where people sort of fall apart in the functional model, even though everybody kind of intuitively does it. And the reason they fall apart is they sit down, they don't talk to each other for 2 weeks, well, okay, a week, and then they go to plug it together on the night it's due, and the thing doesn't fit. You got a round peg and a square hole and a hexagonal whatever on the side, and somehow it doesn't actually do what you were supposed to do. Okay? Don't do that. There's another class. I used to teach 152 for a number of years, and there is a particular project team that's kind of burned in my brain from the very final project. They were working very hard. This was a star team, but they had one member who was actually falling behind, and nobody was talking to anybody, so nobody even knew this person was falling behind. And they went to plug it all together the night it was due, and they discovered they had a big chunk missing. Okay, now if there had been any communication even a few days earlier, that team could have sat down and reapportioned work or tried to figure out what's going wrong. There wasn't any communication. Okay, so that leads to my next topic here, which is communication. Okay, now the more people you've got, the more communication. If nothing else, you got n squared possible links. Okay, I suppose that kind of goes without saying, but I should say it. So basically, you've got a problem which grows as n squared, probably grows much worse than that as the number of people in a team. And changes have to get propagated to more people. So if you have one person that's a rogue hacker and they decide to change all the APIs late at night, they need to make sure everybody knows, or disaster is just about to happen. Miscommunication's common, right? Oh, index started at 0? I thought you said 1. Okay, 0. Got a bunch of C hackers in here. So who makes decisions? Well, individual decisions work great because they're fast. Okay, but if you don't tell anybody about these decisions, then you got a problem, right? Group decisions take time. You could sit down and have every decision made by every person in your group, and you'd be taking 2 months to design project 1. Okay, so you've got to figure out some balance between individual and group decisions. If you have a task-oriented system, I guess you could have one person making the decisions. We're going to do A, B, C, D, E, F, G. Okay, it's efficient. It's not really great for group morale sometimes if it's not done properly. If you've got that one person who's decided to take over the whole group, usually that leads to kind of disaster because people start resenting that person. So you've got to be really careful. If you end up in the role as the one person who's in charge of everything, people may not want you to be in charge. So you have to think about this. I'm not saying I'm not saying it couldn't work. It just needs some careful decision making. So designating a system architect, that's kind of task oriented, has some positives in that there's centralized decisions and one person has a whole view of things and they can kind of coordinate the APIs. The downside is it can lead to resentments. You got to be very careful. That lead person better not be clueless. They better have really good people skills, and they better let other people actually do work. Okay? Let me say that last one again. If you're the lead person in some task-oriented group, you better let other people do work. Okay? Any questions on any of this? So what about coordination? So more people mean not everybody can make all the meetings. How many people scheduled multiple meetings that people missed? Okay. You know, when you got 4 or 5 people with busy schedules, getting meeting times can be hard. However, if you don't meet, you're going to run into disaster. So it's very important to figure out meeting times. I had one 162 group a while back where one person was in a whole bunch of extracurricular activities, and there was another person who was busy tutoring all the time, and as a result, the 5 people could never find a time that was common that they could get together. You know, there's some sacrifices that end up having to be made. You know, maybe you meet at weird hours or something, but you got to figure out how to meet. And I will say that it's inevitable that you'll miss meetings. Okay, that'll happen. It's okay. But, you know, an example of what happens when a meeting is missed is there was a time in the past where somebody decided to completely re-implement something in their own way, and this was a way that the rest of the group had gotten together and decided that they weren't going to do, and as a result, you ended up with a bunch of wasted work and being behind schedule. So if you're going to miss meetings, you better have a really clean way of finding out what happened, like meeting minutes or something. Okay, why do we limit groups to 5 people? Well, because I think more than 5, we would never get anything done. That's my experience with Berkeley students. Why do we require 4? Well, because there's a lot of work to do. And you probably want to experience groups to get ready for the real world because they're going to be much bigger in the real world. So some people work in the morning, some people work at night. How many morning people do we have here? Couple? How many night people do we have here? How many afternoon people? Yeah. So that's a problem. Maybe not if you're all mostly night people. Maybe that works well. You all meet in the lab at 2 in the morning or something. I don't know. What about project slippage? Okay, it's going to happen. You're going to think we're going to get something done tomorrow, and it turns out it's not ready yet. Then what? You know, like phase 4, everybody busy not talking, one person way behind, nobody knew till the very end. Too late. What's the answer to this? Other than killing everybody in your group. What? Start earlier, and what else? Communicate. Talk often. You know, why is this under coordination right after communication? You got to keep reevaluating. It's very easy in a group to fall into this, okay, we've got a week, we'll see you guys in 4 days. You know, we'll find out what happens. Well, the problem is 4 days is probably too late. So you should plan on meeting a couple times a week to figure out what's going on. You know, you could be very 2010s about it, and you know, have con calls or something. You know, conference calls using your cell phones. I don't know, but try to have some communication much more frequently than twice a project. And of course, it's very hard to add people to an existing group because you're still trying to figure out how to make your group work. So that's why we try to avoid too much cross-group coordination. Is there any? Are there any questions? How many people knew all this stuff? This is all obvious to everybody, right? Okay, I've got a couple. All right. I suggest after this class you read through the slides just to see how obvious it was. This might help a few things. It might make it work. I don't know. So how do you make this all work so that by the end of the class you've had a great experience rather than one you hope to forget? So people are human. Get over it. They'll make mistakes. They'll miss meetings. They'll miss deadlines. You need to live with it and adapt. Okay, that's certainly true. It's better to anticipate problems than to clean up after them. And Another thing is document stuff. All right, this sounds painful, but if you sit down and you write out what your plans are, or you write out what the group structure is, so you have the group structure contract or something, you know, Joe will do this, Jan will do this, so on, right? The more you document, the easier it is to, for instance, if you forget about something, go back and take a look. Feel free to use SVN to help. You know, make sure that you check in things when they're working, so that when they stop working, you could always like check back out again something that was working. Okay? So why are you documenting? Just to expose decisions, spot mistakes early, estimate progress, so on. All of this stuff can be done with electronic paper. So what do you document? Well, in theory, everything, but of course that gets really painful, and so you figure out kind of what the right balance is there. And standardize. Silly enough, come up with one programming format. What's your variable naming conventions, tab indents, all that sort of stuff. I've already related to you my office mate when I was in grad school, who used to at 4 in the morning go through and rename all the variables in the code and reindent everything. And unfortunately, he'd never get it completely right, so he'd come in the morning and things wouldn't work. All right? That's just a bad idea. Java doc. You know, at the head of functions, you actually put what the calling sequence is. Java doc is actually a comment-based documentation tool that you could use to put at the head of your major functions, and then you can run Java doc over your code and get a set of documentation. It actually is an amazingly painless way to document stuff that you're working in Java. So these are other options. So some suggested documents, I don't know, maybe objectives, goals, constraints, priorities, specs, what are you actually doing? Probably be the first thing you should do. Meeting notes. How many of you took notes at your meetings? Anybody? Okay, notes are a good idea. Like if you were to take electronic notes and post them somewhere where your group can see them, sounds like a good plan. Especially if you're it's the middle of the night, it's 3 in the morning, and you make some major decision, you could put it in the meeting notes or some wiki you're using or whatever it is, so that people that come in the morning can see what happened. Okay, that simple little write a couple of things down could make a big difference between somebody wasting 4 hours in the morning figuring out what was going on and just sort of running with it in the morning. Schedule. What's your anticipated timing? Org chart. I don't know. These all sound silly maybe for something as small as a 5-person group, but it's certainly worth considering, especially if you have some chaos in your group. Okay? Any questions? Now, the only documents we require from you are essentially your design documents, which are supposed to be English level description of your ideas, and then in the final version, what your results were. But these other documents certainly would be useful for you internally. The last thing I'm going to suggest is software tools. Clearly, things like Subversion, CVS, etc., use your revision control as a positive thing. You can check in things when they're working. You can make sure that you could actually branch code if you wanted to. If you've got something that's mostly working, you want to go off in a different direction. There's a lot of things you can do with source control to figure out what's going on. And if you actually use the descriptions of changes when you check in, you know, then it might be clear to somebody looking at your history what you did. You might use automated testing tools. Things like JUnit for unit testing. All right, we were actually, I think we're going to try to make JUnit available on the website. I don't know if we've done that, but we should do that. Let's put up a release just so people can play with it. But these are good examples of things that you use to wrap around some code to test it. Okay? You could, you know, use email and instant messaging as a way of keeping track of things. I mean, whatever. Use tools to the best the way possible. And test continuously. All right? So do your integration tests tomorrow, not the day it's due. Now, wait a minute. How could you do it tomorrow? Well, what you do is you build basic stubs for the code that you don't have yet so that you can at least compile it and maybe run some basic tests against it, right? You can have everybody produce some version of their module that has the right calls, has the right signature on the calling sequences, and that you could actually integrate together and compile. That might be not a bad thing to do, because then if you continuously do that, you can at least compile the thing the night you try to make it work. Okay? Different types of tests. You could do unit testing, where you sort of check each module in isolation. That might be good if you have a module that, like a priority scheduler. Well, you wrap around it something that plugs in a bunch of different tasks into the scheduler and then extracts them one at a time and see if they come out in priority, right? I mean, those are the kind of testing, unit testing that you could do. Other things that are a little more sophisticated is you can actually throw timing bugs and loops against your code. Try to actually screw it up by inserting random tasks that aren't quite what were expected and see if it gives the right result. Okay. So bottom line, test early, test later, test again, test often. Okay. It's very easy to test once and forget it, and then you go to try it in project 3. And of course, if you haven't figured this out, these projects are mostly cumulative. So what you build in project 1, you use in project 2, which you then use in project 3. Okay? And possibly use in project 4, depending on what project 4 ends up being. So, yeah. Any questions on that? So the reason I give this talk here is not so much that you have to follow all of these things, because if you followed everything I said on all these slides, you'd go nuts. But what I'm hoping to do is give you some suggestions of things that you might try to integrate into your groups as a way of sort of making sure you're actually being productive rather than in contention. Okay? Are there any questions about any of the types of organizations I gave or testing methodologies or? No? Okay. Does this seem at least maybe useful to have thought about some of this stuff? How many people thought about any of this kind of stuff before your design doc? Wow. Okay. More people than I would have expected. Very good. Okay. Some administrivia. So project 1 code and final design document are due, well, the code's due Tuesday and the document's due the day after. So that's going to be standard for you guys. If it turns out you ever have a slip day, the document's due the day after the slip day. Okay? The other thing that's also due right away after the slip day, or excuse me, right after the code is group evaluations. We'll talk more about that Monday. Project 2 kind of starts after you finish project 1. So this is, the way we're set up is basically on a 3-week schedule. It's a Tuesday to Tuesday for the rest of the term. Okay? Autograder. So now some of you are going to start wondering about the autograder. So the autograder is not intended to run frequently. So you shouldn't use the autograder to debug. The autograder is like a final regression test. Okay, so for instance, we might have it only running every 4 hours or something. So if you submit twice in 10 minutes, you're not going to get any results for 4 hours. That's intentional. Okay, you shouldn't be using the autograder to test your code. You should be testing your code by testing your code. Yes?
You say you submit 2 within 10 minutes. Our code when we tested the next 4 hours.
Perhaps. Or maybe the last one. So don't assume you can pump the autograder with a bunch of stuff. I mean, that's not the point of it. Okay? Yeah, now, of course, we have had problems in the past with the autograder, and I'm not sure whether it's functioning quite yet, but we'll make sure that that's running. As we get closer to the actual deadline, it'll run more frequently. Okay? But certainly at the beginning, you shouldn't expect it to be running frequently. I hate to mention it, but midterm 1's coming up. All right? I think it's about 3 weeks. It's on the 18th. And we do have a location, which is 155 Gwinnell. It's a 3-hour exam, and it's going to be, actually, it turns out I know for a fact now, it's the 6 to 9 slot. And it should be about a 2-hour exam with 3 hours of time, but sometimes it gets a little longer than a 2-hour exam. There are example midterms up on the handouts page. So they're midterms and solutions. So feel free to go there and take a look. All right, now what's the topics of coverage? Well, everything up to the previous Wednesday, and or maybe stuff on Friday's section, but pretty much the previous week. Okay? Are there any questions on the midterm? It's hard to believe it's only 3 weeks away, but we're progressing our way through the term already. Okay, there's no class, I think I have a bullet on this. So there's no class on the day of the midterm, so basically I'll just be holding extra office hours. You guys can come by and ask me stuff. Oh, by the way, I apologize if anybody came for office hours today. I actually had an emergency that I had to deal with, so I apologize for that. Yes? Are there going to be 2 midterms for this class? I still don't know yet. Do people want 2 midterms or 1 midterm? How many people would like 2 midterms? How many people would like 1 midterm? How many people don't know? How many people are in the 4th category? The problem with 2 midterms is it will cut out extra material, which can be cool. We'll see. I think my tendency is to try to figure out how to fit in 2 just because it gives you an extra time to, or extra way to demonstrate what you know. But right now there's only 1 in the schedule. If there were 2, it would be second to last week of class or something. So it's kind of the way it would work. It gets a little tight because you've got finals and stuff, but you know. Okay. I think that's all I had in Administrivia. Any other questions? Okay, and I'll post extra office hours as we get closer. Okay, so I want to do 2 things in the remainder of the class. So before we take a break, what I want to do is I just want to mention a little bit of C language support, or excuse me, a little bit of synchronization support that's in regular languages that you might encounter. So in C, pretty much what has to happen is people have to build synchronization in libraries or whatever, and so you might actually do something like lock.acquire or whatever. You know, the thing about this, though, is that you have to be a little bit careful because, for instance, if there's some weird condition that happens, you want to make sure to catch it. Okay, so here's acquiring a lock, and then if there's an exception, we release the lock. Whereas if we didn't have this kind of code in here, it's possible that we would you know, cause an exception and get by without releasing the lock. So I mentioned this a little bit. You have to be careful to always be aware when you grab locks that they get properly released. Anybody here ever use set jump or long jump? Yeah, so you're kind of a dying breed. But the thing about set jump and long jump, this is back in C. This is before C++ made this all cleaner. You could do something like this, where A calls B, calls C, calls D, calls E, and B says something called set jump, which is really setting up a pointer to this stack frame. And then C, let's say, acquires a lock, and then you get down to D, and then E causes an exception, whatever that is, and it calls something called long jump, which really just throws out this amount of stack and restores you back to where the set jump was. So it's a way of doing a non-local exit, kind of like an exception in a more modern language. Well, as you can see here, I just long jumped and squashed out the procedure C, which is probably the one that released the lock. Okay, so the thing to know about if you're dealing with synchronization in a language like C is you better be really careful what sort of exceptions and long jumps and all that sort of stuff can happen, because it's possible that you could grab a lock and it just never gets released. Okay? Now, fortunately, most of you are probably not going to be doing something as, yeah, go ahead. It is kind of like a continuation, yeah. except that it's a linear stack frame, so you're a little more limited in what you can do with it. But yeah. OK, let's look at C++. That's a little more functionality. So if you have exceptions in your language, then it's the same problem, but it's easier to fix. So for instance, here, if I have some function, I call lock.acquire, I call foo in here, and then I release, but foo causes some exception and throws an exception. Well, if you notice here, that thrown exception doesn't get caught anywhere in this RTN function, and so basically we're going to throw ourselves out without ever executing the release. OK? And so that's problematic. It's built into the language that you're supposed to be able to do that cleanly, but suddenly you've caused a problem with your locks and releases. So what do you do? Yeah. Yeah, something like a finally. Well, the simplest thing is to do a catch, right? So you might do something like this, try and catch, okay, where you basically say, well, I'm going to try this thing that I know could cause an exception, and then I'm going to catch any exceptions, and if there's an exception, I'm going to release and then throw it out again. Okay, is everybody familiar with this syntax? Yeah, go ahead.
I was going to say, can you also just, in the if exception, or add an extra command to release the lock?
Oh, in here.
Yeah.
The problem with releasing the lock in here is this sort of violates all sorts of abstraction. I mean, because do-foo isn't supposed to know, probably the way you wrote this, that there's even a lock involved. So, I mean, yeah, you could try to release the lock here, but you don't even have a pointer to it, and you're probably not supposed to know about it. So that would be kind of an abstraction violation. Much cleaner, by the way, for those of you that are C++ programmers, is there things like auto pointer. There are some facilities that basically let you allocate something on entry to a procedure with an automatic cleanup if it ever exits, no matter what. And so the auto pointer facility, for instance, can be made to grab a lock, and then whenever you exit return, whether it's on an exception or anything else, then it releases the lock. So if you're interested in this, this is a much cleaner facility to use. And most people that use something like C++ would use this. Okay, and there's several different versions. Auto pointer is one of them, but that's kind of the idea. Java, of course, has the same issue if you have explicit locks that you're using that are outside of the language. That's what these kind of things are. But Java, of course, has support for synchronization built in. So, for instance, here's, if you remember the bank account example, which we started with for synchronization, what we could do is we could say, well, class account has some private data like a balance and so on, and then we have some methods which are, for instance, synchronized methods. And what synchronized means is it means grab the lock associated with the object before this method starts and release it when the method's done. Okay, so the way to read this is as if at the beginning of this you did lock.acquire, and at the end you do lock.release, and it's automatically built into the word synchronized. Okay, and this particular example has none of the problems with exceptions, because it doesn't matter what bad things happen in the middle here. When you finally exit get balance, it releases the lock. Okay, so that's all built into the language. Yeah, question?
They also have the notion of like sleeping and waking.
Yeah, we'll get to that in the next slide here, just a sec. So the thing to ask yourself, though, a little bit is I'm showing you synchronized in a class. And so you may think, well, wait a minute, that class isn't necessarily realized as an object. Right? So where is the lock? Well, it turns out every time you make an account, so every instance of this class object has its own lock associated with it. So when you call getBalance on account 1, it has a different lock than account 2. That's the way this is. Okay, so synchronized has a lock on every instance of an object. Does that make sense, everybody? Now, it also has synchronized statements. Okay, and so the idea is you say synchronized and you wrap some stuff, you put an object in parentheses, and then you have some text. All this says is take the lock associated with that object and grab it when you enter this open brace and release it on close brace. Okay, yeah, question? So the constructors are, well, they don't have to be synchronized because while you're still constructing it, nobody could have one to grab the lock of.
Oh, but it could be if like two objects are being instantiated at the same time, they're both modifying it.
Well, but see, if they're being instantiated, they're the ones that have the lock. If the data structure already exists, it's got a different lock. Right? So you gotta think about which locks are associated where. Okay. Questions? Yeah.
What does happen if you have a premature release where you, in a constructor, add your object to a queue that goes to worker does something?
You mean if you're in the middle here and doofoo gets an exception?
In the middle of a constructor and you pass the reference to yourself out, you're not supposed to do it, but you do it.
Yeah, I don't think you can even do that in principle. I think it's very hard to do. And if you do it, you probably deserve to get bad behavior. No, I don't know whether you can even do that. I'm sure it's not spec'd well if you did. Because you should never pass an object that's partially initialized out, because then it doesn't really fit in the language. Okay, now let's talk about the fact that Java really has monitors associated with every object. Okay, so I was talking to you about the lock aspect. Actually, there's a single condition variable associated with every lock, and they have these methods like wait, okay, where wait takes potentially a timeout value or no arguments at all, and then there's notify and notify all, which are kind of like our signal and broadcast we mentioned earlier, okay, which are used to wake up somebody. Okay, and so basically, here's an example. You might do this. So, for instance, you know, T1 is time.now, and you might say, well, there's no ATM request. I'm going to wait. And if somebody should put a request on there and signal you, then you'll wake up. Otherwise, this wait will exit after the check period and then check time and see if we're timing out. So you can either have wait woken up because somebody signaled you or because the timeout happens. Okay, but this is exactly like the kind of condition variables we've been talking about. It turns out there's just only one per object. So any of the more sophisticated two condition variable things like we did with the readers writers thing last time, you can't do natively in Java. You'd have to build some structure to deal with it. Okay? Questions? Good. And the other funny thing is, of course, not all Java virtual machines are equivalent, so they have different scheduling policies and so on. So sometimes people try to write code that depends exactly on the scheduling policy, and that may or may not be a good thing. OK, so what we're going to do is we're going to take about a 3 or 4 minute break. And actually, any questions on this language stuff? Sorry, I was cutting you off. You can kind of see, by the way, why somebody might say a monitor is a language feature. Well, you know, this language has a monitor, okay, or gives you native support for a monitor. But a monitor is really a programming style. And I want you guys to keep it that way in your brains. All right, let's take a couple of minutes and 3 minutes or so and come back and we'll talk about Deadlock. So the one thing I didn't mention is, even though I just told you about synchronized and wait in Java, you can't use them. So, because you're building your own locking conventions and condition variables and all that sort of stuff. So, but you can use them if you're ever using Java for something other than nachos. So let's switch gears now and ask ourselves, what's a resource? So resources are things that threads need to do work. So examples are CPU time, disk space, memory, etc. And there's kind of two types of resources. One set are preemptible, and the other set are non-preemptible. So what do I mean by that? Well, preemptible is a resource that you can take away. So I can, for instance, take the CPU away from a thread, and the worst that will happen, is that the thread won't make forward progress. Okay? Non-preemptible resources are ones that if I take it away from a thread, it's likely to have bad things that happen. So, for instance, disk space probably has data you care about in it. So if I arbitrarily take your disk space away, you might object to that, right? Or your thread might have problems. A chunk of virtual address space, for instance, if I arbitrarily take that away from you, you might care. An important one is mutual exclusion. If I have grabbed a lock and have now the right to go into some critical section, and I preempt the lock away from you, the problem with that is that the reason there's a lock there in the first place is there should only be one thread in the critical section. And if by preempting the lock, I now allow more than one thing in the critical section, your code invariants are probably broken, right? So a lock or a critical section is a very good example of a non-preemptible resource that we have to be very careful about. So on a different axes, resources can be exclusive or shareable. So for instance, read-only files are clearly shareable. Printers are not shareable during the moment the printer is in use. Okay? So one of the major tasks of an operating system is to deal with resources. And you clearly figured that out, I hope, when we were talking about multi-threading, because we're implying there's some scheduler, and we'll talk about that in a lecture or two, that figures out who gets CPU time. It's handing the CPU resources out. Today we're going to talk about resources in general and start asking ourselves, can we get into situations where too many people are requesting resources in the wrong order and the system gets deadlocked and doesn't make forward progress? Okay? So to do that, we really need to get some terminology. So starvation versus deadlock. These are two terms that get thrown around. Starvation is really a situation in which a thread waits indefinitely for something. So a great example of that is a low priority thread never getting to go because there are always high priority threads in the way. Or we talked about starvation last time with the reader-writer thread example. If there are always writers coming in, no readers get to go forward, right? Those are starvation examples. Deadlock is a very specific type of starvation in which you have a circular waiting for resources. So if you look at this particular graph here, we have thread A is waiting for resource 2. Resource 2 is owned by thread B. Thread B is waiting for resource 1, which is owned by thread A. And I'm assuming these resources are ones that have to be owned exclusively. And you can see that this particular scenario is never going to resolve itself, and we're deadlocked. Okay? Questions? Yeah.
Starvation is not necessarily a bad thing, right? If in your example we have a low priority thread waiting for high priority things, that's not necessarily bad.
Starvation is not by definition bad, but it's often bad. It often reflects a scenario in which you set up the wrong ordering of things and somebody never makes progress. If, on the other hand, that low priority thread was there just to do something else, if it turned out you were completely, had nothing else to do, maybe it's okay that it gets starved because it means you've got stuff to do, right? So yeah, I would say starvation isn't by definition bad, but it's often bad. Follow-up question?
Oh yeah, so like if a high priority thing would be like move the mouse, like update the mousers on the screen. And a low priority thing might be like if nothing else is going on, maybe start an antivirus program.
Right.
So you wouldn't want to interrupt the person moving the mouse so that the antivirus program.
Well, I think rather than worrying about whether you're interrupting somebody or not, I think it's more important to ask whether somebody, a particular thread ever gets to go at all. That's probably the better thing to wonder about. Because clearly there are situations where you don't want to interrupt somebody in the middle of something. That's exactly why we brought synchronization into play. Okay, other questions? So, deadlock is a type of starvation, not vice versa. So, starvation can actually end. There's nothing that says that if you've got a starved situation, things won't change and eventually you make progress. Deadlock can't end because basically we need external intervention to fix this. Does everybody see that? Because what do I mean by wait for? It means that this thread A is not doing anything else but waiting for resource 2, so it certainly isn't giving resource 1 back to the general pot. And the same with resource 1, thread B waiting on resource 1. So we really are in a situation where both threads are stalled waiting for something, and they're never going to release the thing they've got, and we're just stuck in a cycle. Okay, so all deadlock situations have a cycle of some sort involved in them. And the trick is just figuring out what the right cycle is. Does this have a deadlock? Well, let's see. Oh, there's a cycle, yes. Okay. Now, as I'm going to show you next time, we're not going to get to it. Well, we might actually get to it by the end today. There are some cycles which are not deadlock cycles. Okay, just because you've got a cycle doesn't mean you have deadlock. You have to have a cycle that will never resolve. Okay? Questions? Now, what are conditions for deadlock? Well, one thing to note is deadlock's not always deterministic. So here is great deadlock code, right? Thread A does an x.p and then a y.p. Thread B does a y.p and then an x.p. And these two threads are running, doing a lot of other stuff than just these two operations, and only occasionally does thread A grab x.p and then switch over to thread B grabbing y.p, and now we're deadlocked. Only occasionally. So that's kind of unfortunate, right? And then, of course, these you'd probably be releasing these mutexes this way, but this is grab lock, the first lock, and then the second lock, and this is grab the second lock, then the first. That's potentially a deadlock cycle. Does everybody see that? Now, so deadlock doesn't always happen in this code. You have to get exactly the right timing, or wrong timing, I guess. And you've been testing it over and over and over again, and then you release it, and it's running a nuclear power plant, and it locks up just as it's about to melt down, right? These are the kind of bugs that unfortunately are very common in the field because they require extremely specific circumstances in which to happen. And the only way to combat these is either infinite testing, okay, which is kind of hard because it takes a long time, analysis, where you look and you make sure there are no cycles in the lock acquisition that could ever happen. That is probably a good option, but it takes a lot of work to think about. Or a third option is testing in which you throw random timing at it. Remember I mentioned daemons kind of earlier in the lecture. This would be a great example where you got these two threads and you're running them over and over again, and the trick is you change the timing ever so slightly on every cycle, so they try a bunch of different timings hoping to run into the bad one. Okay, and this is the way you often catch these type of bugs. Yes? Yeah, so if you can build a model and do model checking, that's a great way to avoid deadlocks. But that's often very hard to do in general, but if you can do it. Yep. If your system's small enough and the state is clean enough, yeah, model checking is a great way to check this, yeah. So, so one thing is deadlocks always occur with multiple resources, which means that you can't really decompose the problem into smaller ones and find the deadlocks. It's really you have to go head on with the two threads and the two resources in order to detect it. Here's a simple example. You got 2 disk drives, 2 threads. Each thread needs 2 disk drives to function. Each thread gets 1 disk, and then they go to try to get the other one, and they're deadlocked. Okay, we need to have multiple resources, multiple threads to actually even get into that deadlock. If there was only 1 thread, you'd never deadlock. If there's only 1 disk, you'd never deadlock. Okay? Now, here's an example. You got a bridge, except it's one of those 1-lane bridges that show up a lot in the middle of winter around here on Route 1, right, where half of the road is down the cliff. Okay, and so basically what happens is, you got the 2 lanes of traffic, they go down to 1 lane for that brief period of time. Well, this is a potential deadlock if you've got 2 cars, both on the 1 lane section. What's going to happen? Well, it turns out this is actually a resource constraint, right? This van has got this chunk of resource, it needs this one. This car has got this chunk of resource, needs that one, and we've got our cycle again. Okay, so if you know where to look, you can see potential cycles everywhere. Okay, so here each segment of road's a resource. Car must own the segment under them, must acquire segment they're moving into. How do we get out of this deadlock? A tow truck. Well, basically what you're saying is you got to preempt a chunk of road from one of the cars, right? Yeah. So, various things. You could have a tow truck. You could, whatever you do to preempt the resource, you could have Godzilla come in and pull a car off and throw it over the cliff. I don't know. But starvation is possible here as well. What would that be? Well, what if the cars going one direction are really fast and they're able to zoom through here, and you've got somebody who's not very comfortable being close to a cliff? They may never get across. It isn't that there's a deadlock scenario because there's lots of traffic going from east to west. It's just that the west to east traffic is being starved because you've got a driver who's not comfortable with the circumstances. Okay, so basically these ideas of starvation and deadlock are pretty much in lots of places if you just know where to look. Okay, questions? Now, here is a more realistic one. Well, that one was pretty realistic, actually. I kind of hate those 1-lane things because usually it means there's very little road on one side. But here's a wormhole-rooted network, which is actually a situation you find in a lot of multiprocessors. And notice what we've got here. So in a wormhole-rooted network, packets actually look like trains. So there's like a head of the packet, and there's a bunch of flits in the packet. And you actually open up a path as the message is traveling, and you close the path behind the caboose or whatever. And while the packets are using up the network, they're actually taking space just like a train on a track. So this is actually a pretty physical scenario for a network. And what you can see here is we can get into a circular deadlock if this train that's going west to east needs to go south, this train that's going south needs to go west, this train that's going west needs to go north, and this train that's going north needs to go east. You can see that basically we're now deadlocked because this engine can't get on that track, this engine can't get on that track, this one can't get on there, and so on. So we're deadlocked. Okay? Does everybody see the deadlock? So how do we fix it?
If a packet's stuck for too long, just obliterate it.
Okay, so we have another suggestion for the Godzilla solution here, where somebody reaches down and pulls up the train, right? Okay. Yeah, I suppose maybe you back the train up. That might be a little less destructive. What else could we do? So we could somehow break the trains into portions, and then we'd have to make sure that we could hold a complete train on a segment, maybe. Okay. What else? Yeah. So maybe build some extra segments of track. Okay. What else?
Have rules about how each packet train travels.
Say, what kind of rules could you have?
So they always go one direction before going another direction.
Okay. So you've hit on the dimension order solution. So yeah. So we could have rules, which say, for instance, you got to go east-west first and then north-south. Okay. And in order to do that, though, we're going to have to actually build track in a grid that extends in all the different dimensions. But if we make sure that you always go east-west first and then north-south, you're never going to get into a problem, because notice that this train is going south and then going west, so it's violating that rule. It's going south first and then west, whereas if we say they have to go east-west first and then south, north-south, this turn here, that little red one there and that one there, can never exist. Therefore, we can never have a cycle. Therefore, we can't have deadlock. Okay? So basically, by forcing an ordering of the channels, oh, sorry, did you check the train there? There it goes. Okay. So basically, we're forcing an ordering of channels that say you always go east-west first and then north-south. We've effectively disallowed these two turns by rule, and therefore we can't get into deadlock. Now, the reason I bring this up is this is an example of preventing deadlock by definition, or by being very careful about what ordering resources can be requested in. Okay? So back to that x.p, y.p, y.p, x.p example, how could we prevent us from ever getting into deadlocks involving x and y? What would be the ordering rule? Yeah, always grab x, then y. Okay? Surprising. Okay? If you always grab x first and then y, it's never possible to get a cycle. Okay, and you got to think that through, but the only way anybody could ever have y is if they already have x, and therefore they'll make it through and they'll release them. If you have one that has x, they can never be held up by somebody who doesn't have x because they can't hold y. Okay, so basically by putting in the right rules, we can avoid deadlock. Everybody catch that? So removing deadlock by rules is a time-honored tradition, and actually this particular ordering shows up all the time in multiprocessor networks. And so if you were to study how to get deadlock freedom in a multiprocessor network, you would find dimension-ordered networking as one of the first ones they mention. Okay. Let's talk about the dining lawyers problem. Got 5 chopsticks, 5 lawyers, really cheap restaurant. Okay? Rice in the middle. And it's a free-for-all. The lawyer grabs any chopstick they can, and they need 2 chopsticks to eat. So the problem is, what if they all grab 1 chopstick at once? Right? Now we're deadlocked. Why are we deadlocked? Because we know since they are lawyers, they're not going to give up the chopstick they've got. And they need one to make forward progress. So what happens is they all sit there and they starve. Okay, and this is not starvation, this is deadlock. This is starvation that involves deadlock. Okay? So how do we fix the deadlock? Well, one way we can do is make them give up a chopstick, which seems unlikely. The other is make sure that never let, okay, here's a rule. You ready for this? We're never going to let a lawyer take the last chopstick if no hungry lawyer has 2. Okay, now think that through for a second. It seems kind of messy, but what it says is if there's only 1 chopstick on the table, you're never going to allow somebody to take it if nobody else has 2 chopsticks. Okay, now why that rule? Well, if somebody else has 2 chopsticks, we know that they will finish eating, put the chopsticks back. Okay? If somebody, and basically, if, for instance, I'm the one that will have 2 chopsticks, this would also fit. But does everybody see how this rule prevents deadlock? Okay, now that seems like I pulled that completely out of the blue, right? Ooh, never let a lawyer take last chopstick if no hungry lawyer has 2 chopsticks afterwards. If I ask you this on a test, you would clearly come up with this in 2 seconds, right? All right, well, don't fear. That particular solution I gave you there is a special instance of something called the banker's algorithm, which we will be talking about next time, and which you'll hear about in section on Friday. And this is actually, if you take the banker's algorithm, you can boil it down to this statement, and you find out that you can prevent this from getting deadlocked. The high-level bit to see here, though, is in order to prevent deadlock, what we have is we have a monitor, or somebody, a banker in this case, who's watching from above, who says, I'm never going to let you take resources in a way for which deadlock is inevitable. Anytime you're about to do that, I'm going to stop you until those conditions go away, and then I'll let you go forward. And so this monitor, or what we call the banker, by looking ahead and forcing these lawyers to follow this constraint, can prevent deadlock from ever happening. All right, and that's what the banker's algorithm is about, and we'll talk about that. And that's a method of preventing deadlock rather than letting deadlock happen and having to use Godzilla to resolve the deadlock. Okay? So 4 requirements for deadlock to happen at all. One of them is mutual exclusion. So this has to be that only one thread at a time can use some particular resource. Okay, another is hold and wait. We have to have a situation where a thread grabs a resource, holds on to it while it's waiting for somebody else. A third one is that resource can't be preempted, so it's not possible to reach in and steal the resource away. And the fourth one is that there is a circular wait for which there's a set of threads, T1 through N, and T1's waiting for T2, and T2 is waiting for T3, and T3 is waiting for T4, and Tn is waiting for T1. If we've got all four of these conditions, we've got a deadlock cycle. Okay, or I should take that back. If we have these four conditions, we have the possibility of a deadlock cycle. If we don't have all four of these, we do not for sure have a deadlock cycle. We can say there's no way to have a deadlock cycle without mutual exclusion, without hold and wait, without preemption, or without circular wait. Okay? So that's kind of fun. I mean, I guess if you could verify that your situation is missing one of these four, then you know you're not deadlocked. Okay? Questions on these? Yeah.
So you could just always, if your thread needed more than one resource, make it give up the first while it waits for the second or something.
So one thing you could do, so you're basically going after the hold and wait. You're saying if you made a thread always give up one resource while it's waiting for a second one, you wouldn't have hold and wait, therefore you wouldn't have deadlock. So the answer is yes, that's correct. The problem is that oftentimes you need the two resources. But if you could somehow, if you could come up with a system where you could do what you said, then you'd be fine. Well, except that you got to look carefully at what you're doing. You're probably not actually giving the resource out. You're thinking you're holding on to it so somebody couldn't grab it. So, yeah, go ahead. Could you make your lock system intelligent enough to prevent cycles? Yes. In fact, you could make your lock system run the banker's algorithm with a little more information, and you could prevent deadlock cycle. Now, it turns out, we'll tell you how to do that in the next lecture and a half. But what you'll probably figure out is that it's potentially expensive, and you may not want to do that. But yes, you could, in principle, do that. Good question. So let's just introduce you to something that we're going to use next time. I want to show you what a resource allocation graph looks like. So the system model is we have a set of threads, and each of the threads are going to be little pink bubbles with a label in them. We're going to have, that's fuchsia, I guess, on my screen. I guess it kind of is there, too. We'll have resources, which are represented by rectangles. And notice what these rectangles are here. They have dots in them. And the dots are the number of equivalent resources in the system. So here, R1, there's only one of them. R2, on the other hand, has three of them. And when I say I need an R2, I don't really care which one I get. Okay, that's what that three-dot system means there. Okay, and each thread utilizes a resource by requesting it, using it, releasing it. Okay, so that doesn't seem too mysterious. And so what's a graph look like? Well, we know that the graph itself is partitioned into two types of nodes. T is the set of threads in the system. R is a set of resources. A request edge is an edge between a thread and a resource, which means that thread 1 in this case is requesting resource J. And there's an assignment edge which says that resource J is owned by thread I in this case. Okay, so basically this is exactly what we were calling wait for earlier. So this thread is waiting for this resource, and this resource you could say is waiting for this thread because that resource is owned by that thread. Okay, so the wait for the tail of the arrow is the thing waiting for the thing at the head. Okay? So then we can say, like, here's a resource graph. So let's look at this. We've got thread 1 is waiting for resource 1, but it can't get it because resource 1 is owned by thread 2. Okay, thread 2 is waiting for resource 2, but it can't get it because resource 2 is owned by thread 3. And one of the resource 4s is owned by thread 3. And resource 3, there's two possibilities, and one of them is owned by T1 and one of them is owned by T2. Okay, so everybody see how to interpret that? Is this thing deadlocked? Okay, why is this not deadlocked? Say again?
T3 will finish.
Okay, T3 will finish because it's got all the resources it needs. It finishes, it gives them back, gives resource 2 back, then thread 2 can get what it needs, it finishes, and so on. Okay, and then it gives resource 1 back and resource 3, and then thread 1 can finish. Everybody see that? So this graph is not deadlocked. Questions on that? I see a few puzzled looks. How about this? Possibly because it says with deadlock, right? But can everybody see why it's deadlocked? Okay, now people say cycle, but you got to be a little careful about where the cycle is. Notice that the cycle here is T1's waiting for R1, R1's waiting for T2, T2's waiting for R2, R2's waiting for T3, T3 is waiting for R3. Okay, and R3 is not going to get freed because both of them are waiting for threads that are waiting. Okay, so this is actually a more complicated deadlock cycle. But if you were to look closely at this, you would see this sucker doesn't resolve. Now here is a cycle. Is this a deadlock? Well, it says no, but can everybody see why? Yeah, go ahead. Yeah, so T4 could go, put the resource back. Now T3 can get the resource, and it can finish, and then R1 and so on, T3. So this one's pretty easy because both T2 and T4 can finish right off the bat, and then T1 and T3 are able to go. Okay? Now, does everybody see that? Now, hopefully you see an algorithm in here, right? You see an algorithm. So that algorithm is just simulate your way through and say, well, start with all the threads that have enough to finish, let them finish, put their resources back, then see if now new threads can finish, and so on. Right? So we can build a list-based algorithm, which I'm going to toss at you in just a second, but you can see where that's going. So now the question is, how do we handle deadlocks? We've given you a couple of ways to handle them. One is you could let the system enter deadlock and then recover. So this requires a deadlock detection algorithm of some sort to know you're in deadlock, and then some way of forcibly preempting things. Okay, now databases typically have a clean way of forcibly preempting by basically rolling back transactions. Okay, so that's a way that preempting that's not so bad. Another is basically make sure that the system never enters deadlock. Remember the dining lawyers problem where we had that funny rule? That was preventing deadlock from ever happening. And then the other possibility is you ignore the problem. Okay, you assume that deadlocks never happen, and when your system starts acting funny, you make them reboot. Okay? Unfortunately, this is the one that's more commonly used. Okay, certainly with systems that you're likely to use. Okay, so we'll close up very quickly here. Let me show you a deadlock detection algorithm. So if you only have squares of resources where there's a single dot in it, all you have to do is see if there's any cycles, and if there's a cycle, you're in deadlock. It's when you have rectangles with more than one dot that you need something more interesting. And here's an algorithm for you. All right, and I'm going to toss this up now, and we'll explain it more in class on Friday and also on Monday. But notice that if we have a vector that represents all the resources, so there's as many entries as different resources, then free resources is a vector for which you have an entry for R1, R2, R3, R4, and each entry says how many free dots are there. So for instance, if we only have resource 1 and 2 here, the current free resource vector is 0, 0 because both of these are busy. Okay? And every thread has a request vector. Notice that T1 is requesting R1 but not requesting R2. So T1's request vector would be 1, 0. T3's request vector would be 0, 1. Okay? And so on. And then allocations are which one's currently held by the thread. And so then, I'm not going to make you go through this right now, but suffice it to say this algorithm is extremely simple. It's what we just did earlier. Find the ones that can complete, throw their resources back, see if there's any more that can complete. So we basically keep going through this list of uncompleted nodes, and every time we find that the requests fit into what's available, we remove the node from finished because that thread's done. We add its resources back to available, and we go back in the loop. And we know that when we're done and we haven't made any progress, we've got deadlock, Or if we come out and be done and we have nothing left in the list, then we don't have deadlock. Very simple simulation. Okay, so I encourage you guys to stare at this after class. Okay, so in conclusion, let me just give you, we gave you some suggestions for dealing with partners. Start early, meet often, develop good organizational plan, document everything, use the right tools, develop comprehensive testing plan, and add 2 years to every deadline. Okay, so that's not so good. We talked about starvation versus deadlock. So starvation is thread waits indefinitely. Deadlock's a specific type of starvation that never finishes. We talked about the 4 conditions for deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. We talked about ways of addressing deadlock. We talked about a deadlock detection algorithm. And next time, we'll actually talk about how to prevent deadlock by introducing the banker's algorithm. So you guys have a great weekend. Good luck on your code. We'll see you on Monday.